In part 1 of the video on high voltage power diodes, we looked at the silicon based pin diode, which is essentially a bipolar device featuring minority carrier conduction. The biggest drawback of a pin diode was that it has this huge reverse recovery leading to high switching losses. In part 2 of the video, we will look at Schottky diodes, which are unipolar devices or majority carrier devices and have no reverse recovery problems, and therefore they are very well suited for high frequency switching applications. So in this video we will also study why the silicon based Schottky diodes are not well suited for voltages beyond 100 volts or 200 volts, and how the low resistance of the smaller drift region in wide bandgap semiconductors makes it possible to develop Schottky diodes with very high breakdown voltages, well above feet kilovolts. A Schottky diode is formed by having a thin film of metal in direct contact with usually an N-type semiconductor material. So the metal forms the anode and the N material forms the cathode. Now for this metal semiconductor material to have the rectifying property, it is essential that the electrons of the metal have a lower energy level than the electrons in the N-type semiconductor material. So when the metal is brought in contact with the N-type semiconductor material, because of the higher potential energy of the electrons in the semiconductor material, there is a net flow of electrons from the semiconductor into the metal, and as a consequence the metal becomes negatively charged near the junction, and similarly there is a positive charge at the semiconductor, and this forms the depletion region. And in thermal equilibrium, the potential barrier prevents further flow of electrons from the semiconductor to the metal. We can also see that there is no minority carrier, which in this case is holes, involved in the process. There is only flow of electrons, which is the majority carrier, and this is the key difference between the Schottky diode here and the pin diode. Now when we apply a forward bias, meaning a positive voltage applied at the metal terminal with respect to the N-type semiconductor material, so this applied voltage reduces or opposes the built-in potential and makes it possible for the electrons to continue to flow now. Now when we apply a reverse bias to the diode, meaning the metal is negatively biased with respect to the semiconductor, then this increases the built-in potential and stops the flow of electrons. Now the key point to note is that during the on interval there is no stored minority carrier, and therefore in going from this on state to the off state there is no charge to recover. There is no reverse recovery process here, and that's what makes the Schottky diode the clear choice for high frequency switching applications. The key question then is the reverse blocking voltage. What determines the voltage blocking capability? So here is the cross-sectional view of the Schottky diode. At the top is the metal N- semiconductor contact. This is a rectifying contact, and at the bottom you have this N+ with another metal to form the ohmic contact. Now similar to what we saw in the in part 1 of the video on pin diodes, the smaller the doping concentration for the drift region, higher the blocking capability. So therefore the Schottky diodes also have this N- drift region. So the electric field within the drift region is as shown here. So the this is assuming the charge density inside the drift region is uniform, and very similar to what we did for the pin diode in the previous part, we can derive the expression for the breakdown voltage. So the peak value of the electric field can be given by Gauss's law. So this peak value Em would be the total charge, which is charge of an electron, times the doping, the concentration, times the width of the drift region WD, divided by the epsilon, or epsilon naught times epsilon naught. So that is the peak electric field. The voltage is simply the integral of the field. So VBR would be the area of this triangle here. That will be 1/2 EM WD. Now in this equation, substituting for WD from here, we will come up with this expression. So what we see here is, if for a given semiconductor material, if you know the critical electrical field strength, then we can calculate the required doping concentration ND for a desired breakdown voltage rating. So we would make the doping concentration small to get a higher breakdown voltage, but what that results in is it increases the resistivity and therefore the on-state resistance of the drift region, and that is directly related to the forward voltage drop. So the resistance of the drift region is given by this rho times L over A, where rho is the resistivity of this N-type drift region. The length will be the width of the drift region, and the area is this dimension Z times W cell. So the resistivity in turn is given by, as we saw in the previous video, this 1 over Q mu times Nd, where each of those parameters are defined here, the charge and the mobility of the electrons and so on. So then the materials and the designs, those are characterized by this metric called the specific resistance in ohms square centimeter, which is resistance times the cell area, the Z times omega cell. So essentially the specific resistance is simply rho d times WD. Okay, then using the expression that we had in part 1, which is WD is 2 times VBR over E critical, we get this well-known equation for the specific resistance as shown here. In this equation, the VBR obviously is the specification, that is the desired breakdown voltage, whereas these three quantities, those are the characteristics of the material. Now for silicon semiconductor, since E critical is relatively low, and the specific resistance is an inverse function of the cube of E critical, so we see that the on resistance can be very high. That's why for breakdown voltages higher than about 100 or 200 volts, the on-state resistance is so large that it is not practical to have a silicon-based Schottky diode. Here is a sort of a summary slide for state-of-the-art silicon-based diodes. So the first 4 entries in the table, they are different variants of the basic pin diode. So if you want just a standard recovery diode for extremely low frequency applications, then we can get a low forward voltage drop, 1 volt, at the expense of microseconds level reverse recovery time. Fast and ultra fast diodes, they trade off the forward drop slightly higher, 1.35 1.75 volts, to get reasonably low TRR times in the range of several tens of nanoseconds. And these are all high voltage devices up to 1000 volts, versus if you use Schottky barrier diodes, then the voltage rating is limited to no more than 200 volts, and you have almost no reverse recovery charge. And also at low voltages, the forward drop of Schottky diodes is also reasonably low, about 0.3 volts for very low voltage devices in the less than 60 volts, and going up to 0.8 volts near the 100 volts range. So the main point to note from the discussion so far is that the on-state resistance of the Schottky diodes, if you are using silicon, it becomes very high as the blocking voltages become higher. So that leads into the wide bandgap semiconductors, where it is possible to have Schottky diodes at high breakdown voltages without significantly increasing the forward drop. In the expression for the specific resistance, the quantities at the denominator, they are together commonly referred to as Balliger's figure of merit, and this table lists all the parameters needed to calculate this figure of merit for silicon, silicon carbide, and gallium nitride. Of course, the main advantage of silicon carbide and GaN is that they have roughly 3 times the band gap of silicon, and that leads into the critical breakdown field strength to be about an order of magnitude higher for silicon carbide compared to silicon, and about 15 times larger for GaN compared to silicon. So that results in silicon carbide having Balliger's figure of merit 500 times more than silicon, and for GaN even much larger, 2414. So what this means is that we can have a device with extremely low specific resistance using silicon carbide and GaN, and therefore we can build unipolar Schottky devices for high voltage applications. Okay, this slide shows a comparison of a commercial 1200 volt silicon pin diode with a silicon carbide Schottky diode of the same voltage rating. So the dynamic characteristics during the turn off process are shown, and so clearly this dark red waveform, which corresponds to the current of the silicon carbide Schottky diode, it has negligible reverse recovery, whereas the current corresponding to the silicon diode has a peak reverse current which is significantly larger than the forward current itself. It takes a long time to completely recover and reach zero. So this area, so the overlap of this voltage here and this large negative current represents the switching losses and can become very significant at high frequencies. Okay, so here I'm comparing the some of the parameters given in the data sheets of a different set of commercial 1.2 kV silicon and silicon carbide diodes. The top table corresponds to the silicon carbide Schottky diode, and I wanted to highlight first the forward voltage drop. Okay, so these are typical values, maximum values at different junction temperatures. So they range from 1.5 to 3 volts. And if you look at the silicon pin diode, this also here is the forward drop. It also corresponds to somewhere in that vicinity. So they are comparable in terms of their forward drops. Where the silicon carbide excels is in the dynamic characteristics. So as noted here, this is a majority carrier diode, so there is no reverse recovery charge. There is, however, a capacitive charge, and that is given as about 100 nanocoulombs. Versus silicon diode, it has this large reverse recovery charge, which is almost 3000 nanocoulombs compared to 100 in this case. Okay, and also the silicon pin diode has a reverse recovery current peak value of 724 amperes, is the maximum value, again comparable to the nominal forward current. In terms of the reverse recovery time, even though it gives us relatively low values, 35 nanoseconds, but note that this is only given at a forward current of 1 ampere and voltages of 30 volts, whereas the device is rated for 1200 volts and a current of 30 amperes. So if you consider at least half the rated voltage, the reverse recovery time can be in the range of significantly more than 100 nanoseconds. So the main takeaway is that the silicon carbide Schottky diodes far outperform their silicon counterparts for high frequency, high voltage applications. In fact, the silicon carbide Schottky diode is probably the first device to be widely commercialized. They are even at present used in a large number of applications. For example, the power factor correction circuits, the boost diode in PFCs, and several grid connected renewable energy type applications. And in many cases, simply replacing a silicon pin diode by a silicon carbide Schottky diode without doing any other design changes or component changes. This results in about 2% or 3% improvement in efficiency depending on the specifications.